And good afternoon. Welcome to the Cambridge Spark webinar. I'm Raoul, and some of you might be joining us from further than UK, so either good morning to you or good evening. So for those who are joining us today, Cambridge Spark, we provide professional development for data scientists and developers in UK. We run a 6 months program in data science in London. We run various conferences, so do check it out. And what we're going to do today is to talk about Spark and Zeppelin. So if you're ready, put your hands up in the air right now. Excellent. I can't see you, but I'm sure everyone has their hands up in the air at this right instant. So what are we going to talk about? Well, this is a very buzzword compliant webinar. We're going to talk about big data. I know big data is one of those things that is really used a lot by the marketing departments of several companies. Today, even AI is the new buzzword. Well, at Cambridge Spark, we decided to go to the next level. We decided to go with humongous data because we need yet another buzzword. So humongous data it is. And why do we need to care? Well, the outline of this talk, we're going to talk a bit about what really defines big data and why we should care, and really what can we do with it. So there's different tools such as Hadoop and Spark that you may have heard of, so really, really useful for fancy dinner parties. So that's one of the other benefits of coming to this webinar. You have some useful terminologies and words they can throw around during important dinners. So we'll talk about what you can do with those tools. And then, you know, at the end of the day, we're all developers, data scientists, analysts. What gets us going in the morning is dirty code. So we're going to be doing a bit of live coding, trying to learn about the Spark API and how you can use it to process data on your machine and also on a cluster of machines. So we're going to show you how you can scale data processing on a distributed system. So let's get going. So what's big data? Well, you know, I'm sure there's some fans of XXX listening to us today. And there's one great thing that XXX has done to us here is to come up with a great meme. So with big data, we talk about a triple V. We care about the volume, the velocity, and the variety of the data. So what does that mean? Well, volume is really about how much data you've got available. So here's one way to think about it. So let me just check if everyone has a screen share. There we go. So I just want to make sure that everyone has the slides, that they can see them. No, so let me just try that again. So if we go to the Google Hangouts, screen share. I'll share my screen. Fantastic. And hopefully everyone will be able to see some slides coming up. Fantastic. So we're talking about the volume. And volume is really related to how much data you have available. So let's take an example of Facebook. Facebook has 1 billion users. Let's say they produce around 1 megabyte of data each. You know, that's already around 365 petabytes of data per year. So that's a lot of data. How do we store it and how do we process it? Those are challenges that you have to worry about when we talk about volume. So clearly a single machine is not good enough. We're going to need several machines. We're going to have to distribute the data across them. We're going to have to figure out how we can process the data simultaneously and combine it. But on top of that, what if some machines fail? We need to also worry about fault tolerance. Now, volume is not the only concern with big data. Velocity is also important. And that's the idea that not only you've got a lot of data, but it can be coming rapidly to you. So you need to build a system that is able to scale in real time. So if we think about the CERN, they've reported that they have 10 gigabytes of data transferred every single second. So what kind of infrastructure can we build that is able to support that? Twitter recently indicated that they could handle over 3,000 images every second. So think about how many selfies that really is, right, during the World Cup. You need to build a system that is able to cope with all those images at burst as well. Now, WhatsApp was acquired for $19 billion by Facebook, so pretty sexy. And they've got an infrastructure that is able to process 60 billion messages per day. So that's really impressive. Now, the third concern with big data is variety. Now, I've got bad news. For those of you that are fan of Excel spreadsheets, unfortunately, not all data fits in this nice column and row model. If we think about a payroll system that is internationalized, for example, in UK and Japan, there'll be different attributes, there'll be different data that is required to model how to pay an employee or different contractors. So it's impossible to come with a unified model. And that's really the concern with variety, is that there's other kinds of data, including graph structure, a network. How do you represent the connections on your LinkedIn profile or your Facebook profile? How do you represent geographical maps? I would like to be able to query the best restaurants around Cambridge in a specific area. Well, that's something that's really difficult to model using a two-dimensional table. Even things like images and videos, those are clearly not structured data. So there are three concerns with big data, and how do we deal with big data? Well, we've identified that one machine is not enough. It's too slow, it's not able to store the data, it's not going to be able to handle the load. So we need something different. What we could do is to scale up, meaning we take the same machine, but we make it more powerful, more RAM, more hard disk, more CPU. That's great because we've got the same programming model, which means the same code that you run on one machine is still going to work on one machine, provided it's still the same architecture and hardware. Now, unfortunately, this can be quite expensive, and there's diminishing returns as you try and bring more CPU. The bottleneck is going to be the RAM, but if you try to put more RAM, that gets really expensive. So it's not really flexible. Now, on top of that, you've got a single point of failure. If your machine goes down, that's the end of the world. You can't do anything. So we need another trick. And the trick is to scale out. It's the idea that instead of having one friend that we rely on, we're going to have lots of friends. Many friends is always better, more fun. So what that means is you have a more flexible architecture. If one machine goes down, it's not the end of the world. You can rely on other machines. So it's fault tolerant. It's flexible. We've got a nice elasticity property. So if you have a higher load, you just need to add more machine on your cluster. If you have a reduced load, you can reduce the number of machines required. So that's great. It also can be cheaper because instead of having one very expensive machine with diminishing returns, you can get a lot of cheaper ones and distribute the work. Now, there's no free lunch, as we all know. And the downside with this approach is that the code that we wrote before that was working on one machine, how do we actually run this code on multiple machines? And how do we get those machines to coordinate the data between one another? That becomes really difficult. So it's difficult to use. But don't worry, Spark is one of the possible solutions to help you do distributed processing. Now, this graphic here represents all the different big data technologies and systems. It's actually a subset of them, and different companies are making use of it from back 2016. Now, it's really scary because, as you can see, there's a lot going on. But there's the good news. If you want to become really rich and really important, you can become a big data consultant and everyone's going to hire you because no one has a clue what's going on. There's way too much happening at the moment, so it's pretty scary. But one of the solutions that is really popular to deal with big data problems is the Hadoop ecosystem. And I've simplified here a little bit what the Hadoop ecosystem is. And essentially, there's 3 layers. The first thing that is useful if you want to process data is a way to process. Well, it's a way to store and read the data. So you need a file system. And Hadoop provides something called HDFS, which stands for the Hadoop file system. And what that means is that you have a way to have an interface to a file system, but that's distributed. So you may have multiple machines that are storing the data. You don't have to worry about it. You get fault tolerance, you get scalability, and you still have a nice, simple read and write API. But behind the scenes, it's all distributed. So it's like you have the illusion that you're working with one machine, but behind the scenes, you have multiple machines. So the file system is the first layer available in a Hadoop ecosystem. Now, the other thing that we need is a way to manage resources available in our cluster. And that's what a yarn is. So as you can see, there's a lot of fancy acronyms here, and yarn means yet another resource negotiator. So that's a really good one to bring during the dessert and the wine at the end of your dinner. And essentially, it's a bit like a distributed operating system. You've got a ton of RAM available, you've got a ton of CPU, you've got a ton of storage available, but we need something that can coordinate all those resources, and that's yarn. Now, ultimately, you're going to have a business problem, and you're going to have to be able to answer questions for a business problem. You've got some data, and your boss wants you to answer some questions. So we need a way to process that data. Now, in the past, Hadoop MapReduce was kind of like the popular framework to work around those problems. It's a very quite low-level API that provides 2 operations. But with those 2 operations, you can essentially specify a solution for a querying problem. Now, the implementation of the Hadoop MapReduce is fairly inefficient, very low level, so not really friendly to work with. A few years later, Apache Spark came about. And Apache Spark is a new cool kid around the block, and supports multiple operations that are higher level and a more efficient implementations that works directly with the memory of each of the machine in your cluster. So that's kind of like the preferred solution to work with these days. Now, if you're a large corporate, it's not that trivial. You may be using MapReduce for legacy reasons, so it might be difficult to migrate to Apache Spark, and that's why some people still use MapReduce because of legacy. But today, if you have to start a new project, Apache Spark is the recommended tool to use. So what we're going to do in this webinar is to tackle one specific class of problem. We're going to tackle batch processing. And that's the idea that you have some data at rest. It's available on a distributed system, in a database, on your file system, and you want to process it. But because the data is really large, you've decided that using a tool like Spark that will let you do distributed processing is the right way to go. So what you're concerned about is to make efficient use of the resources available in your cluster. Again, the data is at rest. So here's a couple of examples of where batch processing comes handy. So maybe you need to calculate a monthly payroll. So you might have a huge database of all the employees in your company. And as an end of month job, you want to calculate the payroll summary. So that's batch processing. Maybe you want to train a machine learning algorithm. So you've got a ton of training data that needs to be processed. So that data, again, is available at rest. You need to process it in a distributed manner. So that's going to be a batch processing job. For those of you that work in the financial industry, I'm sure you're aware that regulatory compliance is really important. And if you've got a lot of information about trade orders, for example, trade statements, you may want to process them as a batch job to generate compliance reports, which you can then send down the line to another team. So batch processing, again, means you've got data at rest, it's large, and you need to process it distributively. So what are the tools that we're going to use in this webinar to achieve this? We're going to use Apache Zeppelin, and hands down, it's definitely got the coolest logo out of all of them. Though I quite like the Python one too, but Apache Zeppelin is the winner. Cool name, cool logo. And essentially what it is a notebook where you can type code interactively and get the output for your queries. So it's a little bit like a Jupyter notebook, but on steroids. It supports different interpreter out of the box and also some visualizing tools. So, you know, whenever you use Matplotlib and Seaborn and all that kind of stuff, you have to write code. Well, Zeppelin provides some standard functionalities out of the box in a nice, friendly UI, so pretty cool. We're going to use Apache Spark to process the data on a machine and then on a cluster of machines. And Python, obviously, our favorite programming language. So we're going to do a bit of live coding. If you're interested in the dataset that we're going to be using here, it's the Open Library dataset. You can download it. It's about 100 gigabytes, so it's pretty massive, but you can also download a subset. So let's start a Zeppelin notebook. And this is the interface to Zeppelin if you run Zeppelin locally. And what I'm going to be doing here is to create a notebook that we can start to work with. You can choose what language you want to support here. So we're going to be using the Spark engine. So give it a nice name, like what day are we? Wednesday. Fantastic. And this is what we get. So this is a interpreter. So if we write 1 + 2, for example, we get 3. Awesome. So, if you want to figure out what 1 + 2 is, there's no need to use Spark for that. But as you can see, you type some code and you get an immediate output. Now, let's do a quick Python refresher before I introduce you what you can do with Spark and the RDD API specifically. So let's say we've got some sort of JSON entry. So something like name, and some values. I'm pretty hungry right now, so let's go for Oreos. We all love Oreos. And unfortunately, if I look at this this variable here, if I want to get the name, this is not going to work. Unfortunately, because this is a JSON representation of an object, so it's serialized. So I need a way to deserialize this. So we could import the JSON module. We get our entry here. We load it, and now if I access the name attribute, we've got Oreo printed on the screen. Fantastic. So this is kind of a very basic how you can deserialize JSON data. And the reason I'm showing this to you is because a lot of the data you can download or you have access to is often serialized in some format, and JSON is a really popular serialization format. Now, let's take it one level up. So, we're quite hungry. So instead of having one JSON entry, we're going to have multiple JSON entries. So we're going to have a list of them. So let's create a few of them. And, if we just eat Oreos, it might get a bit boring. So let's spice it up. Let's get some peanuts in there and some peanut butter. Excellent. So if I print this array here, what we'll see is that we have a list of strings, which is not entirely useful. What I want to be doing here is to work with the Python object. So what we can do is to say, well, for each JSON entry and the JSON entries, what I want to do is to first deserialize it. So we're going to load the JSON entry. And now I can print the name. Fantastic, we get Oreo, peanut, and butter. Now, this is the Python way of doing things. So what's the Spark way of doing things? Well, if you want to use the Spark API, there's this thing called the Spark context. Sort of magic variable called SC. So if I just show what the content of this variable is, we can see it's a Spark context object. And that's the entry point to the Spark API. So the first thing we can do is to use a method called parallelize. And what it does is to take a Python list entries here. And it returns a mysterious thing called an RDD. So again, lots of fancy acronyms in this webinar. RDD stands for Resilient Distributed Dataset. And that's the idea that we get an abstraction that enables us to work with a data structure that may be local, or it might be living on multiple machines. But we don't need to worry about this because we have an interface to work with that data. It doesn't matter if that data is stored on one machine or multiple of them. We have an interface to work with. So one of the operations available is count. If I say rd.count, we can see there's 3 elements in this RDD. Fantastic, and we know that because we stored 3 elements here. Now, what else can we do? There is a nice operation called map. So in this code example here, essentially what we did was to iterate through each JSON entry, apply this JSON.loads function, and then print it out. So that's a very imperative style of doing things. Spark has more of a declarative and functional way to specify queries because we need a way to abstract the threading model, the processing model. So we take our map here, and what it's going to take is a function that's going to be applied on each element in this RDD. So we get a JSON entry. We're going to say JSON load that JSON entry. And now I can collect it to a list. So let's see what happens if we run this code. What we'll see now is that we've got a list of Python objects. So that's Python dictionary. So that's pretty useful. So let's maybe do another map. Let's chain it. So now we've got entries. And what we want to say is collect the names of those entries. So if we run this, we now have a list of strings. Now this code here, we can be tidied up a little bit. Instead of specifying an animus function, we could straight away pass the loads function because it takes the argument. So as you can see, this is already a bit more declarative way of doing what we're doing before, where you have to iterate through each thing one by one, apply a function, and then decide how to print it out. Now we've got different operations here that abstract the threading model. All right, so that's pretty handy. But in the real world, we're not going to be working with some small Python list that are living in memory. What we're going to have is a massive data set that we need to load up and be able to process. So how can we do that? Well, I've got a file here, which is a subset of the Open Library dataset. And it's represented in JSON entries. So each line in my file is a JSON representation of a book. And as you can see, it's ugly, but it's ugly in a beautiful way because we're going to be able to work with that data in Spark. So the first thing that we want to do is to be able to load up this file. So again, you're going to need the entry point, so sc. And there's another method here called text file. And what that's going to take as an argument is the file to load up. What text file is going to do is to give you an RDD, so a resilient distributed data set, where each line of the file is an element of your RDD. So let's store this in a variable. And let's figure out what the type of this JSON beta is. And as you can see, it's an RDD. So it's not a Python list. It's this new thing from the Spark API called an RDD. So what can we do with that? Well, why don't we find out how many entries we've got? Well, there's quite a few of them already. So it's about 148,000. So that's not very much. We'll see later on how we can work with billions of entries. But at the moment, it's pretty useful. Maybe we want to do a bit of exploratory data analysis. So we like to find out, well, what's the first element in this file here, in this RDD? So first is a method that gives you the information. And as we can see, it's a string. And the string has a serialized JSON representation of a book, something that has a title. So the effect of differentiated marking tools and motivational treatment on figure creativity. Awesome. That sounds like a book that would be definitely very useful before going to bed. So another thing that we can do is to use a method called take. And take returns multiple entries. So if I say take 10, I've got 10 elements. But again, it's all done in JSON. So that's not particularly useful. We're using Python here, so we need to be able to use the language constructs available in Python. So what we're going to need to do is to convert each of those entries to a Python object that we can work with. So you saw earlier that the method called map can be used to apply a function on each entries. So we're going to call map with JSON.loads. And what that's going to return here are all the books entries. Okay. Now, if I do type of book entries, we're going to see that it's still an RDD. It's a special kind of RDD because it's called pipeline RDD. And that's essentially an RDD where you can chain up different operations, but it's still a resilient distributed data set. Now, what we may wish to do with that is, for example, to extract the titles from the book entries. So how can we do this? Well, the first thing that we want to do is to be able to figure out whether the title attribute exists in that entry. So we're going to filter. That's going to take an entry. We're going to say, well, is the title in the entry? So is that key available? And if it is, then please extract it for us. And then finally, we're going to say take the first 10. Okay, so we take our book entries, and again, that is an RDD that has Python objects now. We filter, provide a function that says, well, how do you want to filter? So make sure the key title is available, and then finally extract those values. So if you run this, what we can see now that we have a much friendlier list that we can work with. So we actually get all the titles of different books. I really love this data set because reflects French. No idea what this is about. Comparison of the nominal grouping and sequence brainstorming techniques of creative ID generation. Excellent, beautiful. But as you can see, this API is really friendly because we're already able to chain up different operations. Now, I don't know about you guys here listening, but you know, usually data sets are a bit dirty, right? You don't actually have all the full information. So one thing that I'd like to find out here is, well, what are different keys available in this data set? Is title always available? So what we can do now is to say, well, why don't we extract the keys available? So another operation available is called Flatmap. And that works just like map, but it's useful when the function that you want to pass as an argument returns a list. So in this case, my entry, I want to say, give me all the keys. And keys returns a list. What Flatmap will do is to flatten each intermediate list that will be produced. Then we're going to distinct. So distinct will remove duplicates. And finally, we can collect this information. So if you run this, what we're going to find out is essentially all the keys available in this data set. For example, we've got the title. So that one makes sense. We have publishers. That also makes sense for a book. Now, I would love if someone can tell me what def date actually means. So apparently books are allowed to have a def date. So if anyone works in the publishing industry here, do let all of us know what def date means. So those are all the keys available. But does that mean that all the entries have all the keys available? Well, let's try and find out. So if I take the book entries again, what I would like to return now is how many keys they are. So we're going to take our entry, and we're going to say, give me the length for the keys for that specific entry. So I'm going to find out the number of keys available. So let's get the information for the first entry in that data set. There's 22. All right, what about the first 3 elements? Well, it looks like there's 22 of them every time. What about the first 10? Well, we can actually see that things are starting to be a little bit different, right? Because the first 4 clearly have 22 keys, then we've got one that has 23, then one that has 21. So clearly there's something weird happening here. So another way to find out the information here, what I'm going to do is to count the number of unique keys available in this data set. And apparently there's 77, but it looks like most of the entries are skewed towards the 20s. What about if we take the first 100? Well, we can see that the skew is definitely towards the 20. We've got this weird books. Well, this one has 7. So what would be useful in terms of doing exploratory data analysis is to kind of get an idea of the distribution for all of those keys. So what we want to find out is for each of the keys available, things like title, publishers, how many times do they occur? What are the most common keys that we can expect a book entry to have? So that's quite a complicated query. So let's see how we can tackle this using the Spark API. So what I would like to specify is the count per key. So for each of the keys available, tell me how many times they occur. So we take our book entries. We're going to flat map this. We take the entry. And what we're going to produce here is something a little bit different. So if we take the entry keys, that's going to produce essentially all the keys available for that book. Now we can use map. At this stage, we get a key because Flatmap is transforming all the book entries to provide the keys, so the strings. For each of those keys, we're going to produce a tuple that says what's the key name together with the number 1. Now, this number 1 might seem a little bit odd, but essentially what it's saying is, I've seen this key once. If we produce those tuples for all the keys available in this data set, what we're going to have to do is to simply add all those ones to figure out the count for each of the keys. And there's another operation available in the Spark API to do this. It's called reduce by key. Takes another function that indicates how do you want to process all the values for the tuples for each of the keys. So for example, for title, we want to say, well, I want to add up all the ones. For publishers, I want to add up all the ones. So we're going to say X plus Y. Okay? Now, let's see what we get if we run this. So if I actually print out this count per key here, we get an RDD. So how do we go from an RDD to something that we can understand in Python? We can call the collect method. And what that's returning me now is the number of times we see each of the keys in our data set. So for example, publisher, there is 136,729 times that we see the key publisher. Now, this text here is not really friendly. So let's see what Zeppelin actually provides us to visualize this information in a better way. So let's collect here. What we're going to say here is print me a nice little table with the name and the count for each of the entries here. So for each key and count in the result, we're going to print it up on the screen. I've got a string, that's the name of the key. We're going to have a decimal because that's the number for the count. And let's see what we get as a result. Okay, so here we've got a loop. So let's run this code, and what we can see that Zeppelin is producing a nice little table for us. Amazing. So we get the publishers and the count. And what we can do interactively here is to say, well, I'd like to be able to sort these based on the count. So here are all the band kids around the block. So apparently there's only one entry in this subset of the data that I've got that has a website key available. But what about the largest ones? So things like type, latest revision, very popular, the title as well. Well, what about a histogram? We want to see core graphics. Well, here's a histogram that kind of shows us what are the distribution for all the different keys. Clearly, we've got the key attribute here that is used a lot. The title is also quite important. The type of the book, and maybe some smaller ones say classification. We don't have a lot of entries that have the classification key. So you can see that Zeppelin is a really useful tool for kind of doing interactive programming, to do some explorative data analysis, but it supports Spark interpreter out of the box. We've just seen how we can process the data on a machine. Now let's look at how we can take the same code here, but work with a much larger data set. Let's go humongous data. So to do this, we're going to need a cluster. Now, AWS provides a really cool tool called Amazon EMR. Yet another acronym very useful for fancy dinner parties. And what that really means is Amazon Elastic MapReduce. That's going to enable you to set up a cluster of machine to process some raw data that you've got, some logs, some big JSON blurb, and it's set it up with a standard stack out of the box. So Spark and Hadoop would be set up for you. So if you sign into your console, you'll be presented with this interface. So that's the AWS interface. And you've got EMR available. And EMR lets you set up a cluster of machines. So I've set up a cluster already here, but if you want to set up your own, you just click Create Cluster. You give it a nice name. So, my cluster is not exactly a great name. So we're going to go humongous cluster. You can decide what the stack should be. So we want Spark, we want Yarn, Ganglia, which is useful for monitoring the resources available in your cluster, and Zeppelin, which is the interactive notebook that we used. You can decide what instance type you want to have. So for example, something like an M3X large. So if you're curious what all of those means, then just go to the AWS documentation and you'll find out that a M3X large, essentially a machine that has around 4 virtual cores and about 16 gigabytes of RAM available. You can go bigger if you want, depends how much money you have, but let's stick to something cheap, agile, and flexible, the M3X large. Now, once you've done that, you decide how many instances you want to have in your cluster. So something like 16, for example. So 16 times 16 will have 256 gigabytes of RAM available to play with. You can set up a key pair, so in case you want to SSH to the master machine. And then you create your cluster. And after a minute or so, boom, you've got all that power available in front of you. Now, you'll be presented with this screen. So that means your cluster is ready to go and you can start to work with. There'll be a few different links available. First one is Zeppelin. So if I click on it, then essentially it presents you with the Zeppelin interface. You can create a notebook. So webinar notebook. You decide what interpreter you want to have. So Spark is set up. And here you can start writing some queries. So we'll come back to that in a second. What are all those other links? There's also Ganglia. And Ganglia is really cool. For those of you that are monitoring geeks, what Ganglia really lets you find out is the resource utilization of your cluster. So how much CPU is being used, how much RAM is being used, so aggregated in the cluster machines. And you can also kind of deep dive into each separate machine on your cluster. So you might be seeing some spikes here, and that's because before the webinar, I was kind of playing around with Spark a little bit, setting up the demo, and you can see that the resource is being used quite heavily. It's been fairly quiet over the last few minutes. So let's have some fun. Let's process a large data set using EMR. So how are we going to do this? Well, I've got another data set that is set up on a service called S3. So S3 is, if you will, a little bit like HDFS, but for AWS. And I've got a file here called the OLCDM.json, which is the Open Library dataset. It has 92 gigabytes of data. So clearly, my poor little MacBook here, it's going to take a while to process all of this data. And this is why I've decided to go distributed. I've got this raw data. I haven't indexed it. I just want to specify a couple of queries as a batch job and get the information. So we're not specifically writing anymore to this file. We're just going to be focusing on the reads. So how can you interface Spark with an S3 resource? Well, so I've got a little notebook setup here. And what I've specified is, given the PySpark interpreter, please load this data from the S3 URL that says the bucket is humongous data and the file is called OLCDM.json. So again, that's a file that has around 100 gigabytes of data. And when I run this code, finding out how many entries there are, Spark suddenly is doing some work. It's coordinating with all the machines in my cluster, trying to find out how many entries there are. And we get a really nice and friendly progress bar here that's going to tell me when the result is available. But let's take a look a little bit at what Ganglia would show us. So if I go back to the EMR interface, to my cluster that I've set up, and I'm going to look at how the resources are being used. As you can see, there is a massive spike here of CPU. We can see that suddenly the cluster is being used heavily. Each of the machines is starting to do some work. So if we go back here, it took around 1 minute, and we find actually the count available in this data set is around 120 million entries that we can work with. That's not too bad. Now, we may wish to do some more interesting queries. For example, finding out how many books have the statement Charles Dickens. So, what that means here, we would like to find out how many books Charles Dickens has written, or how many times Charles Dickens is being specified in the by statement key, really. So if we run this query here, again, we're going to get a nice little progress bar. So obviously, this query is more expensive from a CPU point of view in comparison to just figuring out the count. We need to do some JSON transformation. We need to do some predicate filtering. We need to remove duplicates. So this is going to take a couple of minutes, but this is a great power that you get with Spark. If you work on your notebook locally, you figure out a couple of queries on a subset of your data and you're quite happy with it, and then suddenly you want to find the exact answer, then you can use Spark as a tool to distribute that processing across a cluster of machines. So we're just going to let this run for a little bit and come back to that later. But hopefully, I've convinced you that this is really beautiful. We don't have that problem where our code that was working on one machine doesn't work on multiple machines. It does now, because we've got an interface through Spark, through the RDDs, that enable us to specify different queries where the threading model is completely abstracted away. We don't care if it's one machine or multiple of them. It's still the same beautiful Python code. So let's let this run, and we'll come back to it in a couple of minutes. Now, I just want to introduce a few notes just to wrap up the webinar. So what we've done here is not really optimized at all, right? We get this raw data. We take Spark as just a distributed processing engine, but there's better things that we can do. First of all, instead of using this raw JSON format, we could convert that into a format that is a bit more friendly for querying, something like Parquet, which is a columnar storage format, and there's also support for compression. meaning we could reduce the size of the data set, meaning that would reduce the network communication requires between different machines as well. So Parquet is definitely an interesting way to go, and I would recommend that. Things like queries like finding out just the title in the books lends itself really well to a columnar design. So if you use Parquet, you get lower latency for your queries. Now, Spark also supports Spark SQL and data frames, meaning that you can actually write SQL queries instead of this kind of Spark RDD Python API. So if you're familiar with SQL, then the migration overhead to using something like Spark is really low because there's support for SQL. But more importantly, there is explicit knowledge of the schema of your data. So with a data set, clearly there is a schema because there is things like revision, there is a title, so we can exploit that to have more efficient queries. Now, if you're really concerned with latency, then you might want to look at approximate querying systems. And those are really, really interesting research. It's the idea that if you want to query terabytes or petabytes of data, but you're not really concerned with the exact answer. At the moment, all the Spark queries we've written, we're really concerned with the exact answer. Then a trick is to query a sample of that data within a confidence interval. And that's a really beautiful trick because, in certain kind of business problems, for example, finding out the number of clicks on a particular website or the number of visits, I don't really care about the exact number. I'm quite happy to get a rough estimate, as long as I get a rough estimate really quickly. And that's what approximate querying system lets you do. You can query terabytes and petabytes of data, but it's not going to be the accurate answer. It's going to be being queried over a sample. Now, at the moment, all we've done was really concerned about volume and batch processing. But if you're concerned about velocity, there's a ton of really cool frameworks available these days, and Spark Streaming is one of them. There's more concern about the latency, so the data coming in real time, and you like to enrich the data or process it. Kafka is also popular with Kafka streams that were added also recently. So I would encourage you to look at those tools if you're concerned about velocity and building an infrastructure that then cope with real-time load. Now, just to conclude this presentation, as you can see, Spark is a distributed processing framework. You write some queries in Python or in Scala and Java as well. There's support for other programming languages. But as data scientists, Python is a favorite tool. But a lot of companies use Scala because it provides static type checking, so reduce the scope for bugs as well. So that's definitely something I would recommend looking at. It's really simple to specify ad hoc processing queries. And Amazon EMR provides you with that infrastructure to set up a cluster of machine in a really simple way. And you may be wondering, is that really expensive? Well, not really. Let's take a look at the prices for all of those machines. So we were using the M3 X large machines. And you can see that costs around $0.2 per hour. So if you set up a cluster, it costs less than a sandwich really to use for about an hour and have some fun with. So let's go back and we can see that it took around 4 minutes to find out old books where Charles Dickens is in the by statement key, and we figure out how many distinct book titles there are, around 866. So not too bad for a little bit of Python code. So hopefully you had fun with this webinar. So if you're interested in more webinars, check out the webinar page. We've got a great webinar coming up on exploratory data analysis in Python. If you are curious about how you can use pandas and Seaborn and all those tools to visualize the data, we've got another webinar coming up in November if you're curious about things like Parquet and Avro. So file formats that are more suitable for big data, so you get more efficient querying and more efficient storage. So do check this out. And for those of you in UK, We do have a conference coming up in London on the 20th to 22nd October. So it's a great opportunity to network with professionals in the space. It's running in partnership with the Royal Statistical Society. We have some amazing speakers from the Alan Turing Institute, from Accenture Analytics, from Microsoft, that are going to discuss how data science is used in practice. So do check it out. If you're interested about some more hands-on workshops in Python, this summit gives you some deep dive workshops on exploratory data analysis, but also deep learning and natural language processing. So check it out. And if you'd like us to come to your company and deliver some training courses for your new grads in data science, or maybe you're interested in some more advanced courses, we do provide this service. So check this page, cambridgespark.com/training, and do get in touch with us. So it's been a real pleasure to give this webinar. Hopefully you learned some useful things. I'm gonna take a look at some of the questions, and I will follow up with each one of you offline. So I'll let everybody go back to the family and have a lovely dinner, and see you at the next webinar.